Hello everyone, welcome to this tutorial. My name is Emerson Ahari, I'm a Google Earth Engine specialist. In this tutorial, I'm gonna show you how to get PM2.5 data with 1 kilometer resolution using Google Earth Engine platform and Python API programming. This tutorial is beneficial for those of you who are interested to air pollutant and dust monitoring. So, as you may know, PM2.5 is one of the most useful products that we can use for the dust monitoring. But these data always suffering from coarse spatial resolution. Hopefully, we have a new product already published by awesome Google Earth Engine community catalog, and there is a reference and citation information for this product. Now I'm gonna show you how you can use this data using XEE library in the Earth Engine platform. High spatial resolution in this product allowing us to see the airband textures and the dust variations with a good association. That's actually we never had such kind of details about the airband pollutant and also the dust monitoring before. So now in this tutorial, I'm gonna show you how to get this data and how to analyze using XEE library. Go to Colab environment and make a new notebook. The first step belongs to importing necessary libraries. Let's import Earth Engine libraries like EE, GEE map, and also X-array as XR. The X-array is a kind of library allowing us to deal with multidimensional satellite data with array format. I will show you how it works. And another library is XEE library that recently developed by the Google community that allowing us to bring Google Earth Engine data into X-array format that extends our capabilities to apply machine learning technique on satellite data. Then import the XE and run a code. After a few moments, the process of importing libraries is done and then click to clear selected outputs. So now we need to establish a connection between Colab environment and the Google Earth Engine because we want to use Earth Engine capabilities to deal with the satellite data. Earth Engine start with authentication process and then initialize account information. Project name refers to the account project information that you will be finding through the account information in the code editor, upper right side, go to project info, and here is your cloud project name. Every user has own cloud project name that you can copy and paste it into the code. The next parameter, the next argument is OPT-URL. If you open a browser and search about XEE and Google Earth Engine platform, you will find the a GitHub page in this address, including a detailed instruction about how to work with XEE library. And here you can find the OPT URL address. Just copy and paste it. Let's run. The Colab asking you permission to access to your Google Earth Engine account. Now the permission granted by the user. Just follow these steps as I'm doing like this. So initialize. Okay, something is wrong. There is a typo here. So let's Type it again, initialize, and let's run. Project is wrong, sorry. There it is. Let's run again, and now connection established. From now on, we can use Google Earth Engine capabilities to call and process the satellite data with image and image collection formats. Before going further, I need to identify the region of interest. So, new variable, map created. So, from GEE map, call map function with a satellite base map, just like this. Let's run the map, and after a few moments, you will have a user interface allows you to select your region of interest using existing drawing tools. This tutorial, I'm gonna focus on Tehran, the capital of Iran, a very big city here with over 10 million people residents that always suffer from air pollution. So now I'm gonna show you how to use this dataset for the Tehran as the region of interest in this tutorial. But this tutorial is not limited to only one specific location or one simple example. You can use this data and product for all around the world, and you will be able to apply a various kind of analysis on the introduced data in this tutorial. Let's use the rectangle tools to draw the region of interest. So there it is. In the next step, I'm gonna actually convert the rectangle to a variable. We need to have the rectangle as a variable to define the region of interest and bounds the satellite data based on. ROI sets to from map, select the last feature, convert it to a geometry just like this, and run. The ROI is available as a polygon with 5 vertices. Everything is fine. In the next step, I need to actually call the high resolution PM2.5 data. The dataset link attached below this video on description box and my YouTube channel, and you can find it there. So, as you can see, there is a citation and reference for this dataset. If you want to use this dataset for your own research or project, it is necessary to address the citation in your report. So, this dataset actually available and actually released for the Google Earth Engine thanks to the efforts in awesome Google Earth Engine community catalog that they are working very perfect and providing several or unlimited satellite data in addition to Earth Engine data catalog that allowing us to have more capabilities in remote sensing data analysis. Okay, this product available in 3 temporal frequency, the daily, monthly, and yearly. I'm gonna show you how to deal with this data in with different frequencies. So for example, let's start with the daily format. Okay, the daily collection, the first Earth Engine image collection, just copy the collection snippets, make a parenthesis, here it is, and then make a filter date, actually to filter your data from 2017 to 2022, for example. So let's run. The daily collection called into in the Colab environment. Now, if you get a print from daily call, you will see that our 1822 elements available for this period of time with image collection format. The image collection, as you can see, is a list of images with one band and also including couple of properties or information about the product. Now in this step, I'm gonna convert the image collection format into a multi-dimensional array structure. So how to do this? Let's make a new variable, a daily dataset, sets2, call xr library, and bring the open dataset. I'm gonna convert the daily collection into daily datasets. Couple of arguments necessary here. For example, engine must be set to EE, CRS, EPSG 4326, and the next region of interest ROI, and scale the pixel size sets to 0.001. The CRS or coordinate system is WGS84, and this is a unique ID for all around the world. This is a geographical coordinate system, and spatial resolution is based on degree in this coordinate system. So in this way, scale number 1 shows 100 kilometer and 0.1 10 kilometer, and this value shows 1 kilometer resolution for a pixel size, or 1 kilometer size for each pixel. Let's run the daily datasets. Now you can see the image collection converted to a multi-dimensional format, the daily datasets. As you can see, we have a multi-dimensional structure including time, longitude, latitude, and one variable that is the main band including these information and values. So in the next step, I'm gonna get the average of PM2.5 in this area and see how it varies from one day to another day during the time period. So daily average sets2 gets the daily data set and calculate the average. So the average dimension should be lat and lon because we need to get average over spatial dimension. Let's run, and the daily average is preparing or calculating. So the code example is also available below this video on my YouTube channel in the description box, and if you face with any challenges in the programming, you can compare my code with yours, and then you will find the issue in your code easily and without any challenge. So the daily average calculated. Now you can see we have the average value for the period of time for each day from early 2017 to the late of 2021. So remember that there is a scale factor 0.1 for this data set. That's why we need to multiply the average value to 0.1, just like this. Let's run again, and you can see the values rescaled based on a scale factor, and this is the PM2.5 concentration and unit value. So in the next step, I'm gonna make a plot. I'm gonna make a Excel file first and then make a plot. How to do this? the daily data frame sets to get the daily average converting to data frame. Let's run. And here you have a data frame that shows the daily average through the time. So how to save it in your system? So it's very easy. Just use .to CSV, just like this. This is daily PM2.5 for your region of interest with CSV format. Go to the local address and you can find it and download without any challenge. Save it as it is without any extra task and open it up into Excel file, and here you can see the daily variation for a long-term data. So it's not a long term, actually for 5 years at least. So in the next step, I'm gonna show you how to plot it here. It is very simple. Just call the daily data frame and make a plot. And here you can see the daily variations of a PM2.5. As you can see here, we have actually a pattern of variation here that shows during the cold season, winter time, in the early months or the late month of each years, such as November, December, January, February. In these months, we have high PM2.5, and in reality, in during the winter time, this city always suffering from very high pollution, air pollution, and also causes a lot of health issues for people who are living in this area. So now you can see how it varies from one time to another time. So in the next step, we want to have a look into spatial variations of PM2.5 for this region. Let's continue with the monthly dataset. Now make a new variable, for example, monthly collection. Sets to here, copy collection snippet here, copy and paste it into the code, and make a filter starting from 2017 to 2023, for example. Let's run, and we have a monthly data set converting to a monthly collection. We want to convert it to a monthly data set. Again, open dataset using XR, the monthly collection imported using Earth Engine and CRS EPSG 4326. Scale again sets to 1 kilometer, 0.001, and the geometry sets to ROI. This is the highest resolution actually uh, offered for the PM2.5 in air pollution studies. That's why having access to such kind of data is really important for actually air pollution study. So in the next step, make a print from monthly data sets. You can see 72 months data available starting from 2017 to ends to 2022. So in the next step, I'm gonna make average of each month. For example, we have couple of January, February, and March, and now I'm gonna do an aggregation for each month and calculate the average of January through the years, average of February through the years. So just make a new variable, for example, months mean sets to gets get the monthly data set and calculate average, this time based on time.months, just like this. Then let's run the code. Something's wrong here. Time.months do not exist. There is a problem here. We need to make a group of months. Let's group the data first based on months and then calculate the average based on the time. That was the mistake in my code. So the average of each month calculating here. Then we can have a preview about or a general view about the concentration of PM2.5 in each month generally. So the months mean including 12 PM2.5, the average of each month through the years. So the band name is band number 1. Let's make a plot based on. So x dimension sets to, or x axis sets to longitude dimension, y axis sets to latitude dimension, call sets to months here because the months or months coordinate explaining the variation or temporal variation of this data. Robust sets to true to avoid outlier values impact on visualization. Call wrap, as we will have a multi-temporal plot, I'm gonna show almost 5 images in each row or 5 maps in each row. The color map, I like to have a combination of orange and red colors. Let's run, and now you can see here the monthly variation of PM2.5. As we discussed earlier, in the winter time and cold season, as you can see, in the January and February or December and November, you can see we have higher PM2.5 for the region of interest. But remember to apply the scale factor because the PM2.5 should be rescaled. So multiply 0.1. Once the calculation is done, we can restart the plotting process. Let's run again. The values range also corrected now, and here it is. From now on you can have access to the average of each month. You can calculate the maximum, minimum, or other statistical operators that is necessary in your work. So now I'm gonna show you how to get export from this multi-temporal map. So let's call the matplotlib, import matplotlib.pyplot as plt. This is the most important library for plotting and visualization process in the Python. Using plt call save fig. We want to save PM2.5 with PNG format. DPI sets to 360, and the next one is BB box inches sets to tight. Guarantees that everything, all the plots element including in the output. Okay, After a few moments, the PNG file is available to download. Let's go to download, and here it is. The PNG file is available with the high quality, and here you can see the variations, plot, and all other elements. Okay, back to the tutorial. In the next step, again, we want to plot the monthly variations of the variations of PM2.5 over the region of interest. So now we want to have, for example, previously we had here we had a daily data frame or daily average, and now we want to have the monthly average. Monthly average. Get the monthly data set first, not month mean. The monthly data set here is needed. The monthly data set selected. Calculate the mean over spatial dimension including lat and longitude, and multiply to a scale factor. Let's run. The monthly average is available. Make a plot, have a preview. 72 months, 72 average PM2.5. So convert it into data frame, monthly average dot to data frame. Let's run. Here is monthly data frame dot plot. This is the monthly variation. As you can see, in 2017 there is a significant concentration of PM2.5 actually in the winter time, that shows the rate of the pollutant exceeding from the average value in these months. So, and then you can see there is a temporal pattern that shows the higher values in the winter time and lower values in the rest of the months or rest of the years. So now even we can convert it into the annual format without using the annual collection. So for example, here we can have the annual data set equal sets to, so bring the monthly data set first and resample it to annual, time sets to yearly, and get the average through the time. Remember to apply the scale factor. The annual data set is created. So 6 years, time sets to 6. Let's make a plot. Variable name b1. Make a plot. Sets x sets to longitude, y-axis sets to latitude dimension, robust sets to true, and call sets to time, explaining the temporal variation. Call wrap sets to 3. I want to have at least 3 map per row, and the color map combination of orange and red. Let's run, and here it is. You can see the annual variation of PM2.5 in this region. Very high value, very high average in 2017 and very low value in 2022. I don't know, maybe it belongs to COVID-19 or any other condition that may happen in this year. And also the discussing about the reasons behind the high and low values needs to access the other data and information available for this region of interest. I hope you like this tutorial, and I'm suggesting you to use this product for your own research and your own study area. Remember to cite the dataset according to the citation available in this website. And please share this tutorial with other people who are interested to learn about the Google Earth Engine platform. Thank you for your attention.